Weightlessness silently dismantles the human body from the inside out. Astronauts returning from long missions often struggle to stand, their bones brittle and muscles weakened by the absence of gravity. This is the hidden crisis threatening our dreams of reaching Mars and living among the stars. By the end of this, you will understand how a force we usually harness for radiation protection could be the key to creating a stable, artificial gravity for deep space missions. We will unravel how magnetic fields could generate a persistent pull and explore the radical engineering required to build a ship that creates its own sense of down. How far are you willing to see humanity reach into the cosmos? You can see the toll of weightlessness in the unsteady steps of an astronaut returning to Earth. Their body, no longer fighting gravity, has begun to forget how to stand. This is not just muscle weakness or bone loss, it is a full system failure. Without the constant pull of gravity, bodily fluids drift upward, causing pressure in the head that can impair vision. The heart, no longer working against gravity to pump blood, weakens and shrinks. Even the immune system falters, leaving the body more vulnerable to infection. Leading experts in space medicine warn that a multi-year journey to Mars without a solution would deliver a crew to the red planet too physically broken to plant a flag or conduct meaningful research. They would be visitors in body but prisoners in their own weakened forms. This biological crisis is matched by a daily operational nightmare. On the International Space Station, every single tool must be tethered. A dropped screw does not fall. It hovers, a potential hazard drifting into a critical vent. Water does not pour. It forms floating, wobbling spheres that can short out electronics. This is the profound gravity deficit. It is the single greatest physiological barrier standing between humanity and the stars. Before we can embrace the future, we must first understand why the simple solutions of the past have failed us. That classic image of a spinning space station is more than just science fiction. It is a real, physical possibility grounded in the principle of centrifugal force. When a structure rotates, it pushes everything inside outward toward the walls. This push is not gravity itself, but it can feel exactly the same. If you have ever been on a fast-spinning carnival ride, pressed against the outer wall, you have felt a crude version of this effect. In a rotating space habitat, the entire inner hull becomes your floor. You could walk on it, drop a pen and watch it fall, and live a life that feels perfectly normal. The physics is sound, but the practical application is where the dream begins to unravel. The first major problem is a bizarre phenomenon called the Coriolis effect. Because your head is moving at a slightly slower speed than your feet in a spinning ring, it creates a disorienting tug on your inner ear. Simple actions like turning your head or reaching for an object could trigger severe dizziness and nausea. To minimize this, the rotating ring would need to be enormous, perhaps hundreds of meters across, spinning very slowly. Building something of that scale in the vacuum of space presents an engineering nightmare. The structure would need to be incredibly strong and perfectly balanced, a feat of construction requiring immense cost and complex machinery. Aerospace engineers point to the staggering mass of materials that would have to be launched from Earth, making such a project prohibitively expensive for the foreseeable future. While spinning a ship is a theoretical answer to gravity, its sheer bulk and biological side effects make it a clumsy solution. This forces us to ask a more fundamental question. Is there a way to generate a steady, uniform pull without moving a single, massive part? Our search for a more elegant answer leads us directly to the hidden power of magnetism. That same invisible force that aligns iron filings on a table is a fundamental power of the universe. Magnetism is one of nature's 4 primary forces, governing everything from the atoms in your body to the motion of distant galaxies. To grasp how it could one day create gravity, we must first understand its basic language. Picture the magnetic field itself. It is an invisible region of influence surrounding a magnet, a map of its power. We visualize these as lines of force flowing from the North Pole to the South. The density of these lines represents the field's strength. Where they are packed tightly, the pull is powerful. Where they are spread out, the influence is weak. This field is the medium through which magnetic forces act, a silent push and pull across empty space. It exerts a force on any other magnetic object within its reach. But what about objects that are not obviously magnetic? This is where materials reveal their hidden nature. Paramagnetic materials like aluminum or platinum are weakly attracted to a magnet. Diamagnetic materials, however, are repelled. Water, wood, and most organic materials, including the human body, are weakly diamagnetic. They generate a magnetic field in opposition to an applied field, creating a subtle repulsive force. This is the key. If you could create a magnetic field of immense strength, it would push against the diamagnetic materials in your body. Now, how does this push translate into a controlled force? This is explained by the Lorentz force, a fundamental principle of electromagnetism. Think of a boat on a wide, powerful river. The current represents the magnetic field. If you try to paddle the boat across the current, you feel a push perpendicular to your direction of motion. The magnetic field acts in a similar way on moving charged particles, like the ions in your blood and cells, deflecting their paths and creating a net force. The collective response of all these tiny forces within an object is its magnetic moment, a measure of how much it will twist to align with a magnetic field. Physicists clarify that while the force on a single atom is minuscule, the combined effect across the trillions of atoms in a human body within an enormously powerful field could be significant. This principle of non-contact force of a field creating a persistent push is the foundational idea. It transforms magnetism from a simple attraction into a potential platform, a force we could stand upon. That same magnetic shield designed to block cosmic rays could become the very floor we walk on. Think of a spacecraft wrapped not just in a protective bubble, but in a carefully sculpted force field of immense power. Researchers developing magnetic shielding against radiation are already working with incredibly strong fields generated by superconductors. These are materials that, when cooled to extreme temperatures, can carry immense electrical currents without any resistance, creating magnetic fields thousands of times stronger than a common refrigerator magnet. Now push that idea further. What if we could shape that field not as a simple bubble, but with a precise internal geometry? By arranging superconducting coils in a specific configuration, we could theoretically create a magnetic landscape within the crew compartment. The field's strength would not be uniform. It would be far more powerful along one surface, like the deck beneath an astronaut's feet, and grow progressively weaker toward the ceiling. This gradient is the essential ingredient. Remember the weak diamagnetic nature of the human body. In the presence of this intensely layered magnetic field, every atom in your body would experience a subtle push. Because the field is stronger below you and weaker above you, the net force would be a persistent, gentle pressure downward. It would feel like a continuous tug toward the deck, a sensation eerily similar to gravity. This is not about magnets sticking to your shoes. It is about the entire volume of the ship being filled with an invisible force that interacts with your very molecular structure. The technology shifts from a passive shield to an active environmental controller, a system that defines which way is down. One integrated system could solve the two greatest hazards of deep space travel. The same superconducting coils that deflect lethal radiation could generate a stable, artificial gravity field, eliminating the need for spinning structures and their disorienting effects. This dual purpose transforms the economics and engineering of a Mars mission. Instead of building two massive, independent systems for protection and gravity, you build one. The immense energy and material investment suddenly serve a double duty, making the entire spacecraft lighter, simpler, and far more efficient. But to make this leap from a tantalizing theory to a working prototype, we must confront an immense challenge. How do we generate a magnetic field powerful enough to lift a human without lifting the entire ship off its assembly line? The sight of a frog hovering serenely inside a magnet is not a magic trick. It is a real scientific demonstration of diamagnetic levitation. Every single material, from a living amphibian to the water in your cells, possesses this weak, repulsive property when exposed to a magnetic field. For the frog, an immensely powerful magnet creates a field gradient so steep that the upward push on its diamagnetic tissues precisely counteracts the downward pull of Earth's gravity. The creature floats, suspended by invisible forces. This same fundamental principle applies to the human body. We are mostly water, a distinctly diamagnetic material, and our tissues are a complex collection of organic molecules that all share this characteristic. Under normal conditions, the force is so incredibly faint we never notice it, but the theoretical foundation for artificial gravity rests on amplifying this negligible push into something substantial. Imagine standing inside a spacecraft where the magnetic field is not uniform. It is intentionally designed to be incredibly strong at your feet and progressively weaker at your head. In this layered force environment, every single atom in your body experiences a slight repulsive force. Crucially, the push is stronger from below than from above. The difference between these two forces, however minuscule for a single atom, adds up across the trillions of atoms that constitute a human being. The cumulative effect is a net force pressing you gently but persistently toward the deck. Biophysics experts clarify that this would not be a series of tiny tugs on individual cells. It would be a uniform, whole-body pressure, a field-induced force that acts on your entire mass at once, much like gravity itself. This is the pivotal shift in thinking. We are not using magnetism to pull on metal implants in your bones. We are using it to push against the inherent physical nature of your biology. Your own body becomes the medium through which the artificial gravity is felt. The goal is not to levitate you, but to anchor you. The challenge lies in the staggering field strength required to generate a force equivalent to Earth's gravity. Current estimates suggest it would demand a magnetic field thousands of times more powerful than anything we routinely use in medical MRI machines. Creating such an intense field gradient is the monumental engineering hurdle we must overcome. Yet the promise is profound. If we can master this, the system would be seamless. There would be no spinning sections, no changing Coriolis forces. The direction of down would be defined by an invisible, stable field, and your diamagnetic body would simply respond, allowing you to walk, work, and sleep with a constant, familiar tug. This subtle interaction between field and flesh is the silent cornerstone of the entire concept, suggesting that the key to conquering weightlessness has been inside us all along. That persistent push toward the deck is not a single, overwhelming force, but the sum of countless tiny interactions. Think of it as standing on a ramp where the magnetic intensity grows steadily stronger beneath your feet. This spatial variation in field strength, known as a gradient, is the entire secret. In Earth's gravity, the pull on your head is essentially the same as the pull on your toes. It is a beautifully uniform field. To mimic that sensation, we do not need a uniform magnetic field. We need the opposite. We need a field that is intensely powerful at the floor and grows progressively weaker toward the ceiling. Within this carefully crafted magnetic landscape, every diamagnetic molecule in your body, from the water in your cells to the proteins in your bones, experiences a repulsive push. Because the field is stronger below you, the upward push from that direction is slightly more powerful than the weaker push from the field above you. The difference is small for one molecule, but it adds up across the trillions upon trillions of atoms in your body, resulting in a net force that presses you continuously toward the deck. Physicists often illustrate this with a simple analogy. Picture a ball resting on a perfectly flat, level surface. It goes nowhere. Now place that ball on a hill. It immediately rolls downward from the higher elevation to the lower one, driven by gravity. In our magnetic scenario, the strength of the magnetic field is the elevation. Your body, like that ball, naturally moves from the region of weaker field, the magnetic low ground, toward the region of stronger field, the magnetic high ground. The spacecraft's deck becomes that magnetic mountain, and you are perpetually, gently rolling down its slope. This is the elegant principle that could replace spinning wheels with silent, stable force fields. But generating a hill for a ball is one thing. Engineering a magnetic mountain range vast and stable enough to fill an entire crew compartment, a gradient that must be perfect and unwavering for years on end, is a task of almost unimaginable complexity. How do we build a hill that never erodes inside a ship traveling to another world? The magnets inside a hospital MRI machine are engineering marvels in their own right, generating fields powerful enough to image the soft tissues of the human body. To create artificial gravity, we would need to scale that technology to an entirely new level, wrapping an entire spacecraft habitat in a magnetic cocoon thousands of times more powerful. This leap in scale introduces a cascade of formidable challenges. The first and most critical component is the magnet itself. Ordinary electromagnets, the kind you might find in a junkyard crane, would be utterly useless here. The electrical resistance in their copper wires would cause them to overheat and melt under the immense currents required. The only viable path forward lies in superconductivity. Superconducting magnets are the heart of this concept. They are coils made from special materials that, when chilled to temperatures colder than the void of deep space, lose all electrical resistance. This allows them to carry a colossal, perpetual current in a closed loop, creating an incredibly stable and powerful magnetic field without constantly consuming vast amounts of power. But achieving and maintaining that state is a monumental task in itself. The most common high-temperature superconductors still require cooling to around -320 degrees Fahrenheit, necessitating a complex and robust cryogenic system on board the ship. The magnet assembly would be a massive, fragile structure, a web of supercooled coils that must be perfectly protected from the slightest external heat. The power required to energize such a system in the first place is staggering. While a steady-state superconducting magnet consumes little power to maintain its field, the initial energy input to charge it is astronomical. We are talking about energies comparable to a small city delivered in a controlled surge. For a deep space mission far from the sun, massive solar arrays would be insufficient. This points directly to the need for an onboard nuclear fission reactor, a compact and powerful energy source capable of meeting this immense demand. Propulsion engineers working on next-generation spacecraft emphasize the brutal trade-offs involved. Every kilogram of magnet mass, every watt of power, and every liter of coolant directly competes with fuel, life support, and scientific payload. A heavier spacecraft requires more propellant to reach its destination, creating a vicious cycle of increasing mass and cost. The engineering puzzle is not merely about generating a strong field. It is about generating the strongest possible field with the absolute minimum of mass and power, a challenge that pushes the very boundaries of material science and spacecraft design. Yet, even if we solve the puzzle of power and magnets, another invisible threat emerges, one that could silently dismantle the entire system from within. The walls of this deep space home would not be passive barriers. They would be alive with a silent, immense force. Picture a cylindrical living module where the entire outer hull is lined with a network of superconducting coils. These are not just bolted on, they are woven into the ship's very skeleton, a fundamental part of its architecture. The direction of down is no longer arbitrary. It is a fixed line of magnetic force pointing directly toward the deck. This single, unwavering vector dictates every aspect of the interior design. Workstations are anchored to what is now definitively the floor. Bunks are oriented so that crew members lie parallel to the field lines, allowing for restful sleep with a gentle, familiar pressure. A table placed in the center of the room would be perfectly normal, but a shelf mounted high on the curved wall would feel like a steep, tilted surface. The entire layout must be ruthlessly efficient, conforming to this new, invisible topography where up and down are defined by physics, not by intuition. Every material chosen for the interior becomes a critical engineering decision. Furniture, tools, and storage containers must be fabricated from rigorously non-magnetic substances. Aluminum composites, certain plastics, and ceramics would become the standard, replacing the commonplace steel screws and iron alloys we use on Earth. Even a single stray piece of ferromagnetic metal, like a forgotten steel wrench, could become a dangerous projectile, violently accelerating toward the nearest superconducting coil. Beyond safety, materials could be engineered to enhance the field itself. Integrating layers of diamagnetic or superconducting materials into the floor could help shape and reinforce the magnetic gradient, making the artificial gravity field stronger and more uniform. This is a holistic design philosophy where every object, from a chair leg to a food container, is evaluated for its magnetic properties. This powerful magnetic environment presents a constant, invisible threat to the ship's own electronic nervous system. The very computers that control life support, navigation, and communication are vulnerable. A field strong enough to simulate gravity would easily erase data storage, induce catastrophic currents in microchips, and render standard displays useless. The solution is a fortress within a fortress. Critical electronics would need to be housed in their own shielded compartments, perhaps nestled in the very center of the habitat, wrapped in layers of a metal like mu metal, a specialized alloy designed to absorb and redirect magnetic fields. Wiring throughout the ship would need to be twisted pairs or coaxial cables designed to cancel out induced currents. This creates a strange duality inside the vessel. You could walk across a magnetically induced floor, then step into a shielded control room where the field is near zero, a small sanctuary of normalcy within the storm of magnetic force. Even the most basic functions of life support must be completely reimagined. Plumbing cannot rely on gravity. In this new environment, water would be pushed downward by the magnetic field, but this force acts on the water itself, not on the pipes. Engineers would design a hybrid system using the magnetic push to assist pumps in moving water and waste through non-magnetic piping. Air circulation faces a similar puzzle. Convection, the natural rising of warm air, would still occur, but it would now be shaped by the magnetic gradient. Ventilation ducts and fans would need to be carefully placed to ensure a consistent mix of air, preventing deadly pockets of carbon dioxide from forming simply because the air was too magnetically heavy to rise. The entire habitat becomes an integrated biological and physical machine, where the artificial gravity is not an isolated feature but the core environmental condition that dictates the function of every other system. This is the ultimate goal: to create a vessel where the crew does not endure the technology, but lives within it so seamlessly that the wonder of walking to the breakfast table feels utterly ordinary. The first draft of a magnetic gravity ship exists not in steel but in pure mathematics. Long before a single gram of superconductor is chilled, the entire concept is stress-tested inside a virtual universe governed by the laws of physics. This is the domain of computational physics, where scientists build intricate digital twins of the proposed habitat. They start by defining the geometry, feeding the exact specifications of the superconducting coils and the crew compartment into the simulation. The software then calculates the invisible architecture of the magnetic field, plotting every contour of force and precisely mapping the gradient from the powerful deck to the weaker ceiling. This is not a static picture. The models are dynamic, revealing how the field might fluctuate if a crew member moves, or how it interacts with every object placed inside the habitat. The core of this digital experimentation is a technique called finite element analysis. Think of it as slicing the entire virtual spaceship into millions of tiny, interconnected cubes. The software solves the complex equations of electromagnetism for each individual cube, then assembles the results to show the grand, overall behavior of the system. This allows researchers to identify hotspots, areas where the field might be too weak to be effective or dangerously strong, potentially warping the hull or creating unsafe pockets of force. But the magnetic field is only half the story. The true test is how it interacts with the human body. This is where the simulations become extraordinarily complex. Researchers model the flow of blood, a fluid rich with iron-carrying hemoglobin, through virtual arteries and veins. How would this magnetic landscape affect the heart's work? Would it alter circulation in the brain or the extremities? Other models focus on the vestibular system of the inner ear, the delicate organ that gives us our sense of balance. They simulate the tiny, floating crystals and fluid within its canals, predicting whether the magnetic forces would create a disorienting tug or a stable, gravity-like signal. These digital experiments are crucial for uncovering physiological side effects no one could predict with a simple thought experiment. Could the field induce subtle currents in the nervous system? Would it change the way our cells communicate? The simulations provide the first vital clues. Every run of the model generates terabytes of data, a river of numbers that tells a story of success or failure. This data directly guides the iterative design process. If a simulation reveals a dangerous fluctuation in field strength near a sleeping quarters, the engineers can go back to the digital drawing board. They can tweak the coil arrangement, adjust the power, or change the compartment's shape, then run the simulation again to see if the problem is solved. This cycle of prediction and refinement transforms a bold idea into a viable engineering blueprint, saving years of development time and billions of dollars by catching catastrophic flaws in the safety of the digital realm. The path from this abstract code to a functioning prototype, however, demands a new class of materials that do not yet exist. perhaps the most elegant path to artificial gravity lies not in choosing one technology, but in weaving them together. Picture a future spacecraft that does not rely solely on a massive spinning ring or an impossibly powerful magnet. Instead, it uses both in a delicate dance. The entire ship rotates, but very slowly, generating a mild centrifugal force equivalent to maybe a third of Earth's gravity. This gentle spin provides a foundational pull, a constant background reminder of which way is down. Then, layered on top of this rotational force, a carefully tuned magnetic field activates. This is not the overwhelming field needed to generate a full gravity on its own. Its role is more subtle, more surgical. The magnetic gradient is precisely calibrated to augment the spin's pull, adding just enough extra force to bring the total sensation up to a full Earth-like gravity at the deck. This hybrid approach dramatically reduces the engineering burden. The magnetic system no longer has to do all the work, so its power requirements and physical mass can be scaled down from the monumental to the merely formidable. But the synergy goes even deeper. Remember the disorienting Coriolis effect, that nauseating tug caused by your head and feet moving at different speeds in a spinning ship. The magnetic field could be strategically shaped to counteract this, by creating a slightly stronger repulsive force around an astronaut's head level. The field could provide a stabilizing push, dampening the fluid sloshing in the inner ear that causes dizziness. It would act as a dynamic gyroscope for human biology, making the slow spin feel perfectly smooth and natural. This is the true power of the hybrid model. It leverages the proven, brute force physics of rotation to handle the bulk of the work, while employing the finesse of magnetic sculpting to solve the biological side effects that have always plagued spinning designs. The result is a system where the whole is far greater than the sum of its parts. One technology covers for the weaknesses of the other, creating a stable and comfortable environment that neither could achieve alone. This pragmatic fusion suggests that our first artificial gravity ship may not be a monument to a single breakthrough, but a masterpiece of integration. Yet, even a perfectly balanced hybrid system must face the ultimate test of time and distance. How would the human body itself respond to living inside this combined force for years? Our bodies are masters of interpretation, constantly translating physical forces into a coherent sense of reality. Stepping into a magnetic gravity habitat would be a profound test of that ability. The initial moments would likely be a period of intense sensory confusion. Your inner ear, the body's built-in gyroscope, is exquisitely tuned to detect linear acceleration and the pull of gravity through the movement of tiny fluid-filled canals and microscopic crystals. It expects a certain kind of signal. The constant, subtle push of a magnetic gradient would be a new and unfamiliar input. Your brain, receiving this strange signal, would scramble to make sense of it. The conflict between what your eyes see, a stable room, and what your vestibular system feels, a persistent whole body pressure, could easily trigger a wave of disorientation and nausea, a condition we might call magnetic adaptation syndrome. It would be a form of space sickness, but with a unique magnetic cause. The question is not whether the body would struggle at first, but whether it could learn. The human brain possesses an incredible quality known as neuroplasticity, the ability to rewire its own neural pathways based on new experiences. Think of the first time you put on a virtual reality headset. Your senses rebel, but after a short time, your brain accepts the new rules of the virtual world. Experts in space medicine believe a similar adaptation would occur here. After several days or weeks, the brain would likely stop flagging the magnetic push as an error. It would learn to integrate this new force with visual cues, eventually accepting it as the new, unquestioned definition of down. The sensation of gravity would become real because the brain itself would make it so. This neurological adaptation is just the first layer. The long-term effects on the body's structure are even more critical. In microgravity, the skeleton, no longer bearing weight, halts the natural process of bone remodeling. Osteoblasts, the cells that build bone, become idle, while osteoclasts, the cells that break it down, continue their work. The result is a slow, steady erosion of bone density, a condition similar to osteoporosis. In a magnetic gravity environment, the constant pressure on the bones would provide the mechanical loading they desperately need to stay healthy. While the force is electromagnetic rather than gravitational, the effect on the cellular level could be nearly identical, signaling the osteoblasts to resume their work. The same principle applies to muscles. The anti-gravity muscles in our calves, back, and thighs, which atrophy so quickly in space, would once again have a constant resistance to work against. The body would not be in a state of perpetual free fall. It would be engaged, anchored, and under a constant, healthy stress. However, experts caution that the quality of this artificial gravity matters immensely. Is the magnetic field gradient perfectly uniform, providing an even pressure across every cell? Or are there microscopic variations that could cause subtle, uneven stresses? Long-term studies on Earth using powerful magnetic fields to levitate small animals have shown promising results for cellular health, but scaling this up to human physiology for years at a time is an unknown frontier. The success of a mission to Mars could hinge on this very question of biological acceptance. The crew's ability to walk confidently on the red planet after a multi-year journey depends entirely on their bodies believing in the artificial down they lived with for so long. This belief is not just a feeling, it is a physiological state built cell by cell, and it must be earned. A wrench forgotten in a pocket is no longer a simple tool. It is a potential cannonball. Inside the magnetic gravity habitat, the single greatest danger is the invisible attraction between the ship's own superconducting coils and any stray piece of ferromagnetic material. Iron, nickel, cobalt, and certain steels would be violently ripped from a crew member's grasp, accelerating toward the nearest magnet with enough force to penetrate a hull or sever a critical cable. The solution is a culture of absolute material control. Every single item brought aboard, from a surgical pin to a food container, must be screened and certified as magnetically inert. The spacecraft becomes a sanctuary of non-magnetic materials, a world built from aluminum, titanium, specialized plastics, and ceramics. But how do you transition from this controlled environment to other parts of the ship, like a shielded command module or an external airlock, where the field might be weaker or configured differently? The answer lies in magnetic airlocks. These are not just physical chambers, but zones of graduated magnetic shielding. Before entering the main habitat, a crew member would pass through a series of checkpoints where the field strength is progressively intensified, allowing for a final scan to detect any hidden metallic contaminants. This process ensures that nothing dangerous ever reaches the full force of the living quarters. Beyond the immediate projectile risk, a deeper, more subtle question looms. What does a field strong enough to simulate gravity do to the human body over years of continuous exposure? We have some clues from workers in industries that use powerful magnets, but nothing on this scale or duration. Primary concern is not the static field itself, but its powerful gradients, the areas where the field strength changes rapidly over a short distance. Moving through these zones could induce faint electrical currents in nerves and tissues. While likely harmless, the long-term consequences for neural function or cellular repair are simply unknown. This necessitates a regime of continuous health monitoring far beyond anything used today. Crew members would wear sensors tracking their vital signs and neurological activity, creating a live data stream to detect even the slightest physiological deviations. The ship's medical bay would be a hub of constant analysis, looking for patterns that might signal the need to adjust an individual's exposure or the field's configuration. And because no system is infallible, emergency protocols must be flawless. A sudden coolant leak in a superconducting magnet could cause a quench, where the coil instantly heats up, loses its superconductivity, and releases the stored magnetic energy in a violent burst of vaporized helium. The fail-safe systems would need to detect this millisecond event and shunt the colossal energy into massive, sacrificial dump resistors, dissipating it as heat before it can rip the magnet apart. Redundant, independent cooling loops and rapidly deployable local shields would be essential to contain any failure. In this environment, safety is not a set of rules posted on a wall. It is the fundamental principle woven into the ship's architecture, the daily routine of the crew, and the very philosophy of the mission. Every procedure, from a spacewalk to a meal, must be choreographed around the invisible, omnipresent force that both sustains and threatens life aboard the vessel. Two paths lead to the same destination, but the journey could not be more different. Rotational gravity relies on the brute force of mechanics, spinning a structure to fling everything outward. Magnetic gravity operates on the subtle interplay of fields and atoms, creating a push from within. To choose between them is to weigh a known challenge against a revolutionary risk. Let us compare them directly, starting with the most fundamental question. How well does each method simulate the constant, uniform pull of Earth? Rotational gravity scores high on consistency once established. Inside a large, slowly spinning ring, the force is steady and predictable, acting in a single direction. However, its effectiveness is entirely dependent on scale. A small, rapidly spinning habitat introduces the nauseating Coriolis effect, making it biologically unusable. Magnetic gravity promises a more elegant solution, a uniform force without any moving parts. Yet its effectiveness hinges on achieving a perfectly smooth magnetic gradient. Any slight fluctuation or unevenness in the field could create strange sensations, like walking across a floor that feels slightly steeper in one corner than another. The engineering required to create that flawless field is at present a monumental hurdle. When we look at complexity, the scales tip dramatically. Building a massive rotating structure in space is a colossal construction project. It requires hinges, bearings, and a mechanism to spin a 1,000-ton habitat without wobbling. While the physics is simple, the execution is a nightmare of moving parts and potential single points of failure. A magnetic system, by contrast, has no moving parts. Its complexity is hidden in the cryogenics, the power management, and the sheer fragility of its superconducting heart. A single micrometeoroid puncture in a coolant line could trigger a catastrophic system failure, a risk a spinning ring does not face. This brings us to the critical metrics of mass and power. A rotational habitat is heavy, requiring immense amounts of material to be launched from Earth or mined in space. Once spinning, however, it needs very little power to maintain its motion in the frictionless vacuum. A magnetic system is the mirror opposite. Its infrastructure could be relatively lightweight, potentially integrated into the ship's hull, but the power cost is astronomical. The initial energy required to charge the superconducting magnets is immense, and while maintaining the field consumes little power, the cryogenic system to keep the superconductors cold is a constant, significant drain. This power hunger points directly to the need for an onboard nuclear reactor, adding its own mass and complexity, safety profiles diverge just as sharply. Primary dangers of a spinning ship are mechanical. A bearing fails, a rotor jams, and the entire structure could tear itself apart. But these are largely understood engineering problems. The dangers of a magnetic ship are more insidious. A stray metal object becomes a lethal projectile. A magnet quench releases titanic forces in an instant. Furthermore, the long-term biological effects of living inside a powerful magnetic field are a giant question mark, whereas we understand the effects of rotation quite well. So where does each technology fit in our future? For near-term missions like a crewed voyage to Mars, rotational gravity seems the more pragmatic, if bulky, choice. It is a known quantity, but when we look beyond to the dream of generation ships traveling for centuries or permanent habitats on airless worlds, the magnetic concept begins to shine. Its scalability is its greatest advantage. A spinning ring cannot easily be enlarged once built. A magnetic field, however, can be expanded or reshaped with software and additional coils, allowing a habitat to grow organically. It offers a vision of a ship that is not just a vessel, but a truly integrated environment, where the same system that protects you from radiation also gives you a place to call home. The choice is not necessarily either-or. The most promising path may be the hybrid, leveraging the steady pull of a slow spin augmented by a milder magnetic field to smooth out the biological rough edges. This head-to-head reveals that magnetic gravity is not a ready-made replacement, but a specialist tool. It is the high-risk, high-reward option for the far future, waiting for a breakthrough in power or materials to tip the scales in its favor. The immense power required to generate artificial gravity is only one side of the engineering coin. The other is the physical substance of the ship itself, the materials that must contain this titanic force without buckling. Imagine the superconducting coils not as simple wires, but as the ship's own circulatory system under a constant, invisible assault. When immense electrical currents course through these coils to generate the magnetic field, the field itself pushes back. This is the Lorentz force, a relentless internal pressure trying to rip the magnets apart from the inside. Standard spacecraft aluminum would be hopelessly inadequate, warping and failing under the strain. The solution lies in a new class of advanced composites, materials woven from carbon nanotubes or reinforced with graphene. These are not just strong, they are incredibly stiff and lightweight, capable of withstanding these colossal forces while adding minimal mass to the spacecraft. The entire magnet assembly becomes a single, cohesive structure, a composite exoskeleton designed to resist its own self-generated fury. But the material's revolution does not stop with structural strength. The true game-changer is the superconductor at the system's core. Today's best superconductors still demand cooling to temperatures hundreds of degrees below zero, requiring massive, complex, and fragile cryogenic plants. The next leap forward is the pursuit of room-temperature superconductors. While a true ambient temperature superconductor remains elusive, each incremental gain is a monumental victory. Every few degrees of warming we achieve in the lab translates directly into a lighter, simpler, and more reliable cooling system for the ship. A high-temperature superconductor that operates at a mere negative 100 degrees Celsius, for instance, could use compact, efficient liquid nitrogen coolers instead of bulky liquid helium systems. This single material advancement would slash the mass, power, and risk of the entire gravity generation system, transforming it from a theoretical possibility into a practical engineering goal. Beyond the magnets and their housing, the ship's interior demands another layer of material intelligence. Picture the deck plating not as a passive floor, but as an active component of the gravity field. We could embed it with smart materials, substances that change their properties in response to an electrical signal or a magnetic field. By applying a small current to different sections of the floor, we could dynamically adjust the local magnetic field gradient. This would allow mission control or even the crew to fine-tune the artificial gravity need to conduct a medical procedure that benefits from lunar gravity. The floor in the infirmary could dial the pull down to 1/6 of Earth's normal. Preparing for a return to Earth after a long voyage, the system could gradually ramp the gravity back up to a full 1G, allowing the crew's bodies to readapt slowly and safely. This dynamic control turns a static environment into a responsive one, tailored to the changing needs of the mission. These material breakthroughs are not emerging from a dedicated space lab alone. The drive for better superconductors is fueled by the quest for nuclear fusion, where containing a star in a magnetic bottle demands even more extreme fields. The development of ultra-strong composites is accelerated by research in particle physics, where the next generation of colliders requires magnets more powerful than any built before. We are witnessing a synergistic convergence. The problems of containing a star on Earth and generating gravity in space are, at a fundamental level, the same challenge. Each material science victory in one field delivers a crucial piece of the puzzle for the other, proving that the path to the stars is being paved by discoveries made right here on the ground. The heart of this magnetic starship would beat with the raw power of a miniature sun. Generating a field strong enough to simulate gravity is an energy demand of almost mythical proportions, dwarfing the needs of any previous spacecraft. Every other system, from life support to propulsion, would become a secondary power consumer compared to the colossal draw of the gravity coils. This forces a stark choice for deep space missions far from the reliable warmth of the sun, where massive solar arrays become useless, glittering sheets of glass and metal. The only viable contender for this role is advanced nuclear fission. A compact onboard reactor could provide the steady, high-density power output needed for years on end, acting as a portable power plant dedicated to creating the very environment the crew lives within. The reactor would not just power the magnets, it would power the concept of down itself. Yet the challenge is not just about steady power, but about managing surges of unimaginable force. Think of the initial startup of the gravity system. It is not a gentle ramp up. It is a controlled explosion of electromagnetic energy, a tidal wave of current that must be channeled into the superconducting coils in a single, precise pulse. The ship's power grid could never handle this directly from the reactor. This is where colossal energy storage systems come into play, acting as a reservoir to smooth out these violent peaks. One leading technology is superconducting magnetic energy storage, or SMES. Imagine a giant superconducting coil, separate from the gravity system, kept in its own cryogenic deep freeze. It would slowly sip power from the reactor over hours or days, storing it as a massive, circulating current in its magnetic field. Then, when the command is given to activate artificial gravity, this entire reservoir of energy could be dumped into the main coils in a fraction of a second, bringing the habitat to life without overloading the primary reactor. It is a battery that stores power not in chemicals but in the silent, intense spin of electrons within a frozen ring. The entire electrical architecture of the ship would be a masterpiece of efficiency. Wasting even a fraction of a percent of power as heat would be catastrophic, adding an unsustainable cooling burden. Every power converter, every distribution line would need to be built from materials and designs that push the boundaries of electrical engineering. The system would likely operate at extremely high voltages to minimize resistive losses, turning the ship's internal grid into a network as potent as a terrestrial power transmission line. This relentless focus on efficiency becomes a primary design driver, influencing the shape of the ship, the placement of components, and the daily routines of the crew. Power management would be the central, unending task of the onboard computer systems, a constant ballet of allocation between the gravity field, the cryogenic plants, and the basic necessities of life. Without a revolutionary leap in how we generate and control immense energy in the void, the beautiful idea of magnetic gravity remains a phantom, a sketch in a physicist's notebook, forever waiting for the power to bring it to life. That subtle pull toward the floor is more than a physical sensation. It is the bedrock of our mental stability. We are born with an innate sense of gravity, a deep, unspoken understanding that down is toward the planetary core and up is toward the sky. This fundamental orientation structures our world, telling us where we are and how we fit into our environment. Now, replace that with a new truth. Down is no longer a direction defined by a planet's mass, but by a manufactured field emanating from a wall of humming, supercooled coils. Your entire sense of place is redefined by technology, a constant, silent reminder that you are living inside a machine. For the first crew, this could trigger a profound psychological disorientation, a feeling of being unmoored from the natural order. The brain's cognitive map, which relies on stable cues like gravity to navigate space, would need to be completely redrawn. A window looking out at the stars would no longer feel like a view from a building, but a portal on a wall with space stretching out sideways. This recalibration of spatial perception would be a constant, low-level cognitive task, potentially leading to mental fatigue and stress, especially in the early months of the mission. The consistency of this artificial field, however, could become its greatest psychological strength. Unlike a spinning habitat where the Coriolis effect can create a nauseating, variable tug, the magnetic pull would be uniform and unwavering. Every room, every corridor would share the same definitive down. This creates a powerful sense of normalcy and predictability. A dropped object falls straight down every time. Water pours predictably from a pitcher. The crew could develop a genuine attachment to their habitat as a stable, reliable home, not a disorienting carousel. This consistent environment allows for rituals and routines that feel reassuringly Earth-like, from sharing a meal around a stable table to the simple, grounding act of feeling your body settle into a bunk at night. The mental comfort of knowing which way is down without exception could be the key to maintaining crew cohesion and morale over years of isolation. The ultimate question is whether the human mind can truly accept a manufactured down as a genuine home. Can a wall become a world? The success of the mission may depend less on the physics of the field and more on the crew's ability to forge a new psychological gravity, a shared belief that this magnetic anchor is as real and as comforting as the one they left behind. A simple metal rod suspended in a powerful magnetic field could tell us everything we need to know. The first experimental phase is not about building a starship, but about answering one fundamental question in a ground-based laboratory. Can we generate a stable, measurable force on an object that mimics the response of the human body? Researchers would start with inert materials, placing samples of water, organic tissue, and bone analogues inside the bore of an immensely powerful magnet. Their goal is to map the precise relationship between the magnetic field gradient and the resulting repulsive force. They need to confirm that the math translates into a predictable, controllable push. Once the physics are verified with inanimate objects, the experiments would progress to living biology. Small animal models, like mice or fruit flies, would be exposed to these high-field environments for increasing durations. Scientists would meticulously study every aspect of their health, from cellular function and gene expression to bone density and muscle retention. do their bodies interpret the magnetic push as a mechanical load? The data from these small-scale life forms would be the first critical indicator of biological feasibility. The final, most dramatic ground test would involve human volunteers. Initially, these would be short-duration exposures, perhaps just minutes long, inside a specialized human-rated magnet. Lying horizontally, a person would experience the strange sensation of a new force pressing them into the support couch. The primary objective is safety and sensory feedback. How does the vestibular system react? Are there any immediate cognitive or neurological effects? Each layer of this terrestrial testing builds a foundational understanding, de-risking the technology one careful step at a time. But the true test does not happen on Earth. The ultimate proof requires the pristine silence of microgravity. A compact, refrigerator-sized module attached to the International Space Station could host the next critical phase. This orbital demonstrator would contain its own set of superconducting coils and a small experimental chamber. Inside, a variety of test objects would float freely, from simple diamagnetic spheres to containers of water and perhaps even small plants or insects. With a flip of a switch, the magnetic field would activate. The moment of truth would be watching those floating objects not just move, but accelerate smoothly toward one wall of the chamber, defining a new down in the absence of any other force. This experiment would measure the field's stability over months, its power consumption, and its resilience to the temperature swings and radiation of low Earth orbit. Success here would provide the first concrete evidence that artificial gravity through magnetism is not just a theoretical concept, but a functional principle. Each successful experiment, from a lab on Earth to a module in orbit, adds another brick to the road, transforming a radical idea into an achievable engineering goal for the first crewed mission to Mars. The true price of a mission to Mars is not measured in fuel or hardware alone. It is tallied in the slow, steady degradation of the human body and the immense resources required to fight it. Every minute an astronaut spends strapped into a treadmill or a resistance machine is a minute not spent on scientific research or mission-critical tasks. This is the hidden economic drain of weightlessness. A magnetic gravity system presents a staggering upfront cost, but its value must be measured against the constant, grinding expense of the current alternative. Developing the superconductors, the cryogenics, and the power systems would require a research and development budget comparable to the largest space projects in history. The price tag would be colossal, a multi-billion-dollar gamble on unproven technology. Yet, this initial investment could be amortized over decades of deep space exploration, paid forward across countless missions to the Moon, Mars, and beyond. The long-term savings begin with the human element. Consider the rigorous daily exercise regimen required on the International Space Station. Astronauts dedicate over 2 hours each day to intense workouts just to slow the rate of muscle and bone loss. This is not optional, it is a medical necessity. Now multiply that time by a crew of 4 on a 3-year Mars mission. You are losing thousands of person-hours that could have been dedicated to geology, botany, or systems maintenance. With artificial gravity constantly maintaining their physiology, that 2 hours of daily exercise could be drastically reduced or even eliminated. The crew transforms from patients in their own rehab clinic into fully productive explorers, their time reclaimed for the mission itself. The financial benefits extend into risk mitigation. Sending a physically compromised crew to Mars carries enormous liability. A broken bone from brittle osteoporosis or a fainting spell from cardiovascular deconditioning could jeopardize the entire mission. The medical monitoring, the redundant life support, and the astronomical insurance premiums for such a hazardous endeavor represent a massive ongoing cost. Artificial gravity dramatically lowers this health risk profile. By preserving crew fitness from launch to landing, it reduces the likelihood of medical emergencies and the complex, weighty equipment needed to treat them. This is where the dual-purpose nature of the system delivers its greatest economic punch. A spacecraft typically needs two massive, independent systems, one for radiation shielding and another for crew health maintenance through exercise. The magnetic approach consolidates these into a single, integrated architecture. The same superconducting coils that deflect cosmic rays also generate the gravity field. You are not paying for two systems, you are designing one. This consolidation slashes mass, simplifies vehicle design, and ultimately reduces launch costs. For a private company like SpaceX, where the cost per kilogram to orbit is a primary driver, this integration is not just attractive, it is essential. The business case shifts from a pure science project to a strategic enabler. The high initial investment is not merely an expense, but a down payment on a future where humanity can work and thrive in deep space, turning the greatest barrier to exploration into a manageable engineering challenge. A multi-generation starship cannot afford to gamble with the health of its inhabitants. For a crew destined to live their entire lives between the stars, the artificial gravity beneath their feet must be as reliable as sunrise on a planet. This is where the magnetic concept reveals its most profound advantage over mechanical spinning. A rotating ring with its bearings and motors would be a maintenance nightmare over centuries, a system prone to wear and failure that no amount of spare parts could fully guarantee. A well-designed magnetic field, once established by its superconducting coils, could theoretically persist for 100 years with minimal intervention. A silent, stable force requiring only a steady trickle of power to maintain its cryogenic heart. The longevity of the entire human colony would depend on this unwavering constancy. Over such immense timescales, the technology itself would evolve. The ship's engineers, born en route, would not be mere caretakers of an antique system. They would be innovators, using advanced manufacturing to grow new superconducting materials or refine the field geometry, making the artificial gravity even more efficient and uniform for their children. The power source would likely be a fusion reactor, a miniature star on board, providing the clean, dense energy needed for generations. This self-contained ecosystem would create an environment utterly independent of the ship's journey. Whether the vessel is coasting at a constant velocity or maneuvering around a cosmic obstacle, the magnetic gravity inside remains perfectly consistent. There is no need to stop spinning to change course, no disorienting shifts in perceived gravity. The interior world is a placid island in the turbulent sea of interstellar space. For a society living in a bottle, this unwavering sense of down provides a psychological anchor, a stable foundation upon which culture, family, and a sense of normalcy can be built across centuries. The children of the stars would never know a world without this magnetic pull, their bodies and minds shaped by a force that allows them to thrive in the void. When their descendants finally step onto a new world, they will do so with strong bones and healthy hearts, thanks to the invisible field that faithfully stood in for a homeworld they never knew. The humming deck of a generation ship is a promise of health, but that promise must first pass through a gauntlet of ethical review. Before any human volunteer steps into that magnetic field, the entire concept must survive the scrutiny of panels like NASA's Institutional Review Board. These committees are not focused on engineering schematics. Their sole concern is the human being at the center of the experiment. Their first and most formidable question is one of fundamental unknowns. How can an astronaut give truly informed consent for a multi-year exposure to a force whose subtle, long-term biological effects are purely theoretical. We can model blood flow and bone density, but can we predict the effect on neural pathways after 2 years of constant magnetic pressure? This gap in knowledge creates an ethical chasm. The principle of informed consent, the bedrock of all human research, requires a clear understanding of potential risks. Here, the risks are themselves unknown, making the consent process a profound challenge. The committees would engage in a brutal risk-benefit analysis, weighing the potential for revolutionary human advancement against the possibility of irreversible harm to the test subjects. For an early mission to Mars, the calculation is stark. Is the known progressive damage of weightlessness a greater evil than the unknown, potentially novel damage of artificial gravity? The answer is not found in physics, but in philosophy and law. International space ethics committees would add another layer, ensuring the mission adheres to global standards for the peaceful and responsible use of space. They would dissect the selection process for the first crew, guarding against any pressure, explicit or implicit, that might coerce an individual to accept undue risk for the sake of a national or corporate agenda. The psychological profiling would be more intense than for any previous mission, ensuring the crew members possess not just courage, but a deep, personal understanding of the uncertainties they are choosing to embrace. This ethical navigation is a parallel mission to the engineering one. It demands that we build a framework of responsibility as robust as the spacecraft itself, proving that our reach into the cosmos is guided by a moral compass as unwavering as the magnetic field we seek to create. The sleek, spinning rings of science fiction stations have trained us for decades to expect a mechanical solution to gravity. We have seen it in our movies and read about it in our books, a visual shorthand for life in space. That powerful cultural image now stands as a subtle barrier to a far more abstract idea. How do you sell the public on a gravity system with no moving parts, an invisible force field pushing you toward the floor? The spinning station is immediate and understandable. The magnetic solution is a silent, unseen push, a concept that lives in equations, not in dramatic visuals. This gap between the familiar fiction and the complex physics could breed public skepticism at the very moment we need overwhelming support. People might ask a simple, reasonable question. If the spinning ring works in theory, why are we gambling billions on this strange magnetic alternative? The narrative surrounding the technology becomes as critical as the engineering. Will it be framed as a dangerous, unnatural experiment, tampering with fundamental human biology using forces we do not fully comprehend? Or will it be presented as the next great leap, an elegant fusion of technologies that solves two problems at once? The answer lies in the art of science communication. We must translate the abstract into the relatable. Instead of talking about magnetic moments and field gradients, we demonstrate the principle with a live frog, peacefully levitating inside a magnet. We use the analogy of a powerful river current pushing against a swimmer to create a directional force. We build transparent demonstration modules for science museums, where visitors can watch water and small objects fall toward a magnetically defined down. These tangible experiences build a bridge of trust and understanding, transforming public perception from confusion to wonder. The story we tell about magnetic gravity will determine its future. A story of innovation and human ingenuity can capture the global imagination, inspiring a new generation of scientists and unlocking the political will and funding required. A story mired in fear and uncertainty could relegate it to the pages of theory, another brilliant idea that never left the laboratory. The final frontier is not just a place, it is a story we are all writing together, and the next chapter depends on the words we choose today. A project to build a magnetic gravity ship is too colossal for any one country to shoulder alone. Its sheer scale, cost, and technological complexity demand a global alliance, echoing the spirit that built and sustained the International Space Station. This is not just a matter of sharing the financial burden, though that is critical. It is about pooling the world's best minds and most specialized technologies into a single, unified effort. The European Space Agency brings decades of expertise in superconducting magnet design, a legacy from particle physics research at facilities like CERN. Japan's Aerospace Exploration Agency could contribute its unparalleled robotics, essential for the delicate, autonomous assembly of the massive coil structures in the vacuum of space. Meanwhile, Roscosmos, with its hard-won knowledge from the Mir station and decades of Soyuz missions, holds irreplaceable data on long-duration life support systems, understanding how to keep a sealed environment functioning reliably for years on end. Each partner would contribute a unique piece of the puzzle, transforming an impossible solo endeavor into a manageable, shared mission. This international framework does more than just distribute the astronomical costs. It spreads the risk, ensuring that a technical or political setback in one nation does not derail humanity's entire progress toward the stars. More profoundly, it reinforces the ideal that space exploration is a unifying human endeavor, a frontier where national borders dissolve in the face of a common goal. The very act of building such a ship together would become a powerful testament to global cooperation, forging partnerships and trust on an unprecedented scale. The vessel itself would be a monument not to one flag, but to the collective ingenuity and shared aspiration of all humankind. This ship would be a slender needle, a transit vehicle designed for the long cruise between Earth and Mars. Its heart is a cylindrical habitat module, a self-contained world for the crew, but it does not spin. Instead, it is wrapped in a dense web of superconducting coils, the source of its artificial gravity. The direction of down is not beneath their feet in the traditional sense, but toward the curved outer hull of the cylinder. One entire wall of their living space becomes the floor, a surface that curves gently upward on either side. Walking into the center of the room would feel like climbing a subtle, almost imperceptible hill, with the strongest magnetic pull always at your feet. The crew's bunks would be arranged perpendicular to this floor, so sleeping feels natural, and a table in the middle of the common area would have a slightly slanted surface, a constant, quiet reminder of the manufactured physics governing their home. Every single design choice is dictated by the magnetic topography, creating an interior that feels both alien and intuitively correct. To generate a stable one-gravity equivalent, the magnetic field gradient needs to be immense. Current estimates suggest a field strength on the deck of around 20 Tesla, thousands of times stronger than a typical refrigerator magnet. This staggering requirement dictates the ship's power source. A compact, onboard nuclear fission reactor becomes non-negotiable, a portable power plant dedicated almost entirely to the gravity system. It would need to generate a steady output in the range of several megawatts, enough to energize the magnets and run the cryogenic plants that keep the superconductors chilled to near absolute zero. The mass of the magnet system itself is a brutal engineering trade-off. The superconducting coils, their composite support structures, and the cryogenic plumbing could easily mass hundreds of tons, a significant fraction of the entire vehicle's weight. This is the price of creating a stable, familiar down for the crew. Every component serves a dual purpose. The same coils that generate the gravity field also act as a powerful shield against cosmic radiation, deflecting high-energy particles that would otherwise bombard the habitat. This integration is the system's greatest elegance. Instead of two separate, massive systems for protection and health, the ship employs one unified architecture. The mass penalty of the magnets is offset by the eliminated need for a massive spinning structure and its complex bearings and motors. This design represents a fundamental shift from a vehicle that endures the hazards of space to one that actively engineers a safe, Earth-like environment within it. This is the blueprint for a new era of exploration, a vessel where the journey itself is no longer a physically destructive ordeal, but a sustainable passage to a new world. The humming magnetic deck of the first Mars ship is merely the first faltering step. Over the next century, this foundational technology could evolve into something so seamless and integrated that we would no more question it than we question the light from a bulb. The first and most transformative leap will likely come from the core of the system itself, the superconductor. Today's need for complex, power-hungry cryogenics will vanish with the arrival of a true room-temperature superconductor. This single material breakthrough would shatter the current engineering barriers. The massive cooling plants would be replaced by compact, efficient power managers, turning the gravity generator from a fragile, high-maintenance beast into a reliable appliance. The mass and complexity of a spacecraft would plummet, making artificial gravity a standard feature on everything from a lunar commuter shuttle to a deep space tug. But the evolution does not stop at mere efficiency. The next frontier is control. Imagine walking from a gym where you experience a full Earth gravity for a heavy workout, into a relaxation lounge where the field is dialed down to the gentle pull of the moon. This is the promise of personalized, localized gravity. Instead of a single, ship-wide field, advanced coil arrays embedded in the walls, floor, and ceiling would create isolated gravity zones. You could have a workstation where tools are magnetically anchored to a table at Mars gravity, right next to a sleeping nook that maintains a constant, healthy Earth normal for bone density. The very architecture of a space habitat becomes fluid and dynamic, capable of reshaping its physical reality to suit any task or comfort level. This fine-grained control opens doors far beyond the spacecraft hull. Back on Earth, the same principles could revolutionize medicine. Patients recovering from severe burns or major surgery could be suspended in a variable gravity field, allowing their bodies to heal without the constant pressure of their own weight. Physical therapy could be conducted in a graduated environment, gently strengthening muscles and bones with precision no water tank or harness can match. In manufacturing, diamagnetic levitation could enable the contactless manipulation of delicate components, assembling microchips or biological tissues in a perfect, containerless float. The initial, clunky system we envision for a Mars mission is the steam engine to this future's silent electric motor. It represents the primitive ancestor of a force that could one day be woven into the fabric of our daily lives. This long-term vision transforms artificial gravity from a life support system into a fundamental utility, as essential as power and water, enabling a civilization that is not just visiting space, but truly living there. The silent threat of weightlessness meets its match in the hum of a magnetic field. Our journey has taken us from the quiet decay of the human body in orbit to the radical idea of sculpting gravity itself from invisible forces. We have navigated the core principles of diamagnetic repulsion and field gradients, understanding how a push could feel like a pull. We have faced the staggering realities of engineering, from the cryogenic hearts of superconducting magnets to the immense power of onboard reactors. And we have pondered the most critical element of all, the human spirit, and its ability to adapt to a world where down is a manufactured direction. The hurdles standing before this vision are undeniably immense, demanding breakthroughs in material science and a deep understanding of long-term biological adaptation. Yet the potential reward justifies the colossal effort. It is the promise of sending explorers to Mars who arrive not as weakened patients, but as robust pioneers, ready to step onto a new world with strength and vitality. This is more than just a new piece of spacecraft hardware. It represents a fundamental shift in our philosophy of space travel. We move beyond merely surviving the hostile void and toward actively terraforming the interior of our vessels, creating pockets of Earth like normalcy amidst the stars. The road to the cosmos is long and fraught with challenges, but with each bold concept we refine, we pave another mile of that path. The future of humanity in deep space may not be found in a spinning carousel, but in the stable, silent resonance of a magnetic embrace. If this vision of our journey to the stars resonates with you, we would love to hear your perspective. Share your thoughts in the comments below and subscribe for more explorations into the ideas that will shape our future among the stars.